Engineering is supposed to make the world safer. Bigger bridges, stronger buildings, more advanced technology. But sometimes one tiny mistake, one ignored warning, or one bad decision can turn human innovation into a complete disaster. In this video we're going to look at 13 of the most terrifying engineering catastrophes in history, from collapsing dams and exploding space shuttles to nuclear meltdowns that changed entire countries forever. Some of the disasters happened in seconds, others were years in the making, but all of them left behind one haunting question. How could this possibly happen? Picture this. It's late at night, April 26, 1986. Most people in the small Soviet city of Pripyat are asleep. Nothing feels unusual, but inside reactor number 4 at the Chernobyl nuclear power plant, something is about to go catastrophically wrong. The engineers on duty weren't trying to cause a disaster. In fact, they were running a safety test. Ironically, a test meant to figure out what would happen if the reactor lost power. The plan was simple on paper. Reality? Not so much. The reactor design, known as RBMK, had a dangerous flaw. It could become unstable at low power levels. Combined it with human errors, operators disabling safety systems, pushing the reactor beyond safe limits, and you get a perfect storm. At 1:23 am, everything spiraled out of control. A sudden power surge triggered a massive explosion. Not just one, two explosions ripped through the reactor. The 1,000-ton lid of the reactor was blown off like it was nothing. Graphite blocks caught fire, and radioactive material shot into the sky. And here's the terrifying part. The explosion didn't look like a nuclear bomb. There was no mushroom cloud. Instead, it was worse in a quieter, invisible way. Radiation. Firefighters arrived within minutes. They had no idea what they were dealing with. No protective gear, no warning. They were fighting a fire that wasn't just fire, it was radiation itself. Many of them would receive little doses within hours. Meanwhile, the nearby city of Pripyat carried on as usual the next morning. Kids went to school, people went to work. No one had been told anything. It wasn't until nearly 36 hours later that the evacuation began. By then, thousands had already been exposed. The Soviet authorities tried to contain the situation, sending in liquidators, hundreds of thousands of workers tasked with the cleaning up radioactive mass. Some shelved debris of rooftops, others buried contaminated soil. Many did it within minimal protection. The long-term consequences were devastating. Large parts of Ukraine, Belarus and Russia became contaminated. Entire villages were abandoned forever. The so-called exclusion zone still exists today, a haunting, frozen in time reminder of what happened. And the human cost is still debated. Immediate death were in the dozens, but long-term effects, cancer, illness, displacement, affected hundreds of thousands, possibly millions. What makes Chernobyl especially chilling isn't just the explosion, it's how preventable it was. A flawed reactor design, poor safety culture, and a system where questioning authority wasn't exactly encouraged. All of that combined into one of the worst engineering disasters in human history. And even today, decades later, Chernobyl is still teaching us a hard lesson. Sometimes the most dangerous failures ain't sudden. They're built slowly into the system itself. Now imagine this, it's March 11, 2011 in Japan. A normal afternoon suddenly turns into chaos when one of the most powerful earthquakes ever recorded, magnitude 9.9, strikes the country. At the Fukushima Daiichi nuclear power plant, the reactors actually do what they're supposed to do. They shut down automatically. So far so good. But the real problem wasn't the earthquake, it was what came next. About 40 minutes later, a massive tsunami over 14 meters high in some areas slammed into the coastline. The plant's seawall? It was only designed for waves about 5-6 meters high, so the ocean just went over it. Water flooded the facility, knocking out backup generators, and that's when things got critical. Nuclear reactors need constant cooling, even after they shut down. Without power, the cooling systems failed, and without cooling, the reactor cores began to overheat. Within hours, fuel rods started to melt. Over the next few days, pressure built up inside the reactors. Hydrogen gas accumulated, and then, boom! Explosions tore through multiple reactor buildings. If you've seen the footage, it's surreal. Massive blasts, buildings disintegrating, and all of it happened in a country known for its engineering precision. But here's the key detail. Fukushima wasn't just a natural disaster, it was a design failure. The plant had known vulnerabilities. Experts had warned about tsunami risk years earlier, but upgrades were slow and assumptions were made, like a tsunami that big probably won't happen, until it did. Over 150,000 people were evacuated from the surrounding areas. Entire towns were left empty. Even today some zones remain restricted. The radiation release was significant, though not as severe as Chernobyl. Still, the ecological and social impact was enormous. People lost homes, communities, and a sense of safety. And globally, Fukushima changed everything. Countries began rethinking nuclear energy. Some shut down reactors entirely. Others introduced stricter safety regulations. What makes Fukushima so unsettling is that everything almost worked. The systems responded to the earthquake. The shutdown worked, but one underestimated factor, the height of wave, was enough to cascade into a full-scale disaster. It's a reminder that in engineering it's not just about what's likely, it's about what's possible. Let's switch scenes out into the middle of the ocean. It's April 20, 2010, on the Deepwater Horizon oil rig, operated by BP. The rig sits in the Gulf of Mexico, drilling nearly 1.5 thousand meters below the water surface. Everything seems routine, until it isn't. Deepwater drilling is incredibly complex. You're dealing extreme pressure, volatile materials, and no room for error. And on that night, a series of bad decisions stacked up. The key issue? Cementing the well. The cement is supposed to seal the well and prevent oil and gas from escaping, but the job wasn't done properly. Warning signs appeared, pressure anomalies, strange readings, but they were misinterpreted or ignored. Then came the blowout. Highly pressurized gas shot up the drill pipe, reaching the rig in seconds. It ignited almost instantly. The explosion was massive. 11 workers were killed. The rig burned for 2 days before sinking into the ocean. But that was just the beginning. With the rig gone, the wellhead on the ocean floor was left uncontrolled. Oil began gushing into the Gulf, not for hours or days, but for 87 days. An estimated 4.9 million barrels of oil spilled into the ocean. To put that into perspective, it became the largest marine oil spill in US history. The environmental impact was devastating. Marine life was coated in oil. Birds, turtles, dolphins, entire ecosystems were affected. Fishing industries collapsed. Coastal communities suffered huge economic losses. And stopping the leak? It wasn't easy. Engineers tried everything. Contaminate domes, top kills, junk shots, many of which failed. Finally, a month later, they managed to seal the well. Investigations later revealed a mix of technical failures and human factors, cost-cutting, time pressure, and a culture that underestimated risk. Sound familiar? Because it's a pattern we've seen before. Deepwater Horizon wasn't just an accident, it was a chain reaction of small decisions that led to a massive catastrophe. And like many engineering disasters, the warning signs were there, they just weren't taken seriously enough. Okay, this one feels almost unreal, like something out of a disaster movie, but it happened, and it might actually be the deadliest engineering failure in history. Let's go back to August 1975 in Henan province, China. The Bankao Dam was considered a major achievement. Built in the 1950s to control flooding and generate power, the design was supposed to handle what engineers called a once-in-a-thousand-years flood. But nature had other plans. A super typhoon, Typhoon Nina, sailed over the region, dumping an unimaginable amount of rain. We're talking about a year's worth of rainfall in just a few days. The dam started taking on more water than it was ever designed to handle. Now here's where things get complicated and honestly frustrating. Some engineers had previously warned that the dam's design wasn't sufficient, but those concerns were ignored or downplayed during construction. At the time, speed and political pressure mattered more than caution. As the water levels rose, communication systems began to fail. Requests to release water were delayed, and when they finally tried to act, it was too late. On August 8, the Bankao Dam collapsed. But it wasn't just one dam. Thousands of dams in the region failed almost simultaneously, creating a chain reaction. A massive wall of water, reportedly up to 10 kilometers wide and several meters high, surged downstream at incredible speed. Entire villages were wiped out within minutes. People didn't have time to react, many were asleep, others had no warning at all. The immediate death toll is estimated in the tens of thousands, but when you include famine, disease and the aftermath, the number may reach over 150,000. Some estimates even go higher. And here's the part that makes it even more chilling. For years, the disaster was kept largely secret. Information was restricted, reports were limited. It wasn't until decades later that the full scale became widely known. What went wrong here wasn't just the weather. Yes, the storm was extreme, but the system failed on multiple levels: engineering design, communication, and decision making. The dam wasn't built with enough safety margin, warnings weren't taken seriously, and when the crisis came, the response was too slow. Bankao is a brutal reminder of something simple. When you're dealing with nature, unlikely doesn't mean impossible. Now this one is different and somehow even more unsettling, because technically the dam didn't fail. In northern Italy, near the Alps, stood the Vajon Dam. At the time, it was one of the tallest dams in the world, an engineering masterpiece, strong, massive, impressive, and completely useless against what was coming. Engineers had built the dam in a narrow valley beneath a mountain called Mountain Top. Even during construction, there were signs that the mountain wasn't stable. Small landslides, cracks, movement in the rock. Some experts raised concerns, but the project moved forward anyway, because again, confidence, assumptions, and maybe a bit of overconfidence in engineering. By 1963, the reservoir behind the dam was full. On the night of October 9, everything changed. A massive chunk of the mountain, around 260 million cubic meters of rock, suddenly broke loose and slid into the reservoir. Not slowly, violently. The impact displaced an enormous volume of water, creating a wave hundreds of meters high. Think about that for a second. A wave taller than skyscrapers. The water had nowhere to go except up and over the dam. Within seconds, it surged over the top and rushed down the valley. The town of Longaron, just below the dam, was completely destroyed. Entire communities were wiped out almost instantly. Around 2,000 people died, and the dam, it was still standing. That's what makes this disaster so eerie. The structure itself didn't break. The engineering of the dam was, in a way, successful, but the bigger picture, the environment, the geology, was misunderstood or maybe ignored. Investigations later showed that the risk of a massive landslide had been known. There were warning signs. Even smaller landslides had already occurred, but the scale of what could happen was underestimated. What John teaches a very specific lesson. Engineering isn't just about building strong structures, it's about understanding where you build them, because sometimes the danger isn't in the thing you create, it's in the ground beneath it. This one is different again. No explosions, no collapsing structures, just gas. Invisible, silent, and deadly. It's the night of December 2, 1984, in Bhopal, India. Near the city stands a pesticide plant owned by Union Carbide. Inside the plant, a highly toxic chemical, methyl isoconate, is stored in large tanks. And that night, something goes terribly wrong. Water somehow enters one of the tanks. This triggers a chemical reaction that rapidly increases temperature and pressure. The safety systems that should have prevented disaster, many of them weren't working. Some were turned off to save money, others were poorly maintained. And pressure builds, the tank begins to leak, and then a massive release of toxic gas into the air. It spreads quickly over the sleeping city. People wake up coughing, choking, unable to breathe, eyes burning, lungs on fire. There's panic, confusion, no clear warning. Thousands try to run, but where do you run from something you can't see? Within hours, thousands of people are dead, and the tragedy doesn't stop there. Hospitals are overwhelmed. Doctors don't even know what gas they're dealing with, making treatment incredibly difficult. In the following days, the death toll continues to rise. Estimates vary, but around 3,000 people died immediately. The total death toll over time was exceed 15 to 20,000. And hundreds of thousands more suffered long-term health effects, respiratory issues, blindness, birth defects. Even today, decades later, the area is still dealing with contamination. So what caused it? A mix of cost-cutting, poor maintenance, and weak safety culture. Critical systems were offline, staff were undertrained, warnings were ignored. Again, a pattern. What makes Bhopal especially disturbing is how preventable it was. This wasn't an unpredictable natural disaster, it was a failure of responsibility, a failure to prioritize safety over profit. and the consequences were felt not just in the moment, but for generations. Alright, imagine this. It's January 28, 1986. Millions of people are watching live TV. School classrooms across the United States are tuned in because this launch is special. For the first time, a teacher, Krista McAuliffe, is going to space. The shuttle, Space Shuttle Challenger. Everything feels exciting, hopeful, historic, but behind the scenes, there is a problem. Actually, several people already knew there was a problem. The night before the launch, engineers raised serious concern about the cold weather. Temperatures had dropped unusually low for Florida, close to freezing, and that mattered because of one small but critical component: O-rings. These rubber seals were used in the solid rocket boosters to prevent hot gases from escaping, but in cold temperatures they became less flexible, less reliable. Engineers warned NASA launching in these conditions could be dangerous, but the launch went ahead anyway. Pressure, scheduling, public expectations. At 11:38 am, Challenger lifted off. For the first minute, everything looked normal. Then, at 73rd seconds into the flight, it happened. A plume of flame appeared on the side of one booster, exactly where the O-ring had failed. Hot gases escaped, weakening the structure. And then, catastrophic breakup. The shuttle disintegrated in the sky, live on television. It wasn't a traditional explosion like in movies. It was a structural failure. The external tank ruptured, and aerodynamic forces tore the shuttle apart. All 7 crew members were lost. The shock was immediate and global. How could something so advanced, so carefully engineered, fail so suddenly? The investigation that followed revealed a lot. NASA engineers had data showing O-ring issues in previous flights. The risk wasn't unknown, but it had been normalized. This is something called normalization of deviance. When a problem happens repeatedly but doesn't immediately cause disaster, people start accepting it as safe, until one day it isn't. The Challenger disaster wasn't just a technical failure, it was a decision-making failure. Warnings were there, concerns were raised, but they weren't acted on. And that's what makes it so haunting, because it shows how even at the highest levels of engineering, the biggest danger isn't always the technology. Sometimes it's the choices we make around it. Now fast forward to 2003. By this point, space shuttle launches had become almost routine. People still cared, of course, but there wasn't the same level of constant attention as in the early days. The shuttle this name? Space Shuttle Columbia, NASA's first operational orbiter. The mission starts normally, but just 82 seconds after launch, something happens. A piece of foam insulation breaks off from the external fuel tank and strikes the shuttle's left wing. At the time, it doesn't seem catastrophic. Foam hitting the shuttle had happened before. Again, normalization of deviance. NASA revived the footage but concluded it probably wasn't a serious issue. The mission continued. For 16 days, everything appeared fine. Experiments were conducted. The crew worked as planned. No one knew that the foam strike had created a hole in the wing, and that hole would become deadly during re-entry. On February 1st, Columbia began its descent back to Earth. As it re-entered the atmosphere, temperatures on the outer surface reached over 1,500 degrees of Celsius. Normally, the heat-resistant tiles and reinforced carbon panels protect the shuttle, but this time there was a breach. Superheated air entered the wind through the damaged area. Internal structures began to fail. Sensors started showing abnormal readings, rising temperatures, loss of pressure. Within minutes, the situation became uncontrollable. At around 60 kilometers above Texas, the shuttle broke apart. Debris scattered across hundreds of kilometers. All 7 astronauts on board were killed. Just like Challenger, the Columbia disaster wasn't caused by a single failure. It was a chain. From strike, underestimated risk, lack of follow-up inspection. NASA had even considered using satellites or other methods to inspect the damage in orbit, but didn't pursue it aggressively. And there's the pattern again. The warning signs were there, they just didn't seem urgent enough. Columbia reminds us that even small damage, something that seems minor, can become catastrophic under the right conditions, especially in extreme environments like space. Now let's bring it back down to Earth. It's December 15, 1967, late afternoon. Rush hour traffic is building on the Silver Bridge, cars bumper to bumper. Nothing unusual, until suddenly the bridge collapsed. Not partially, not gradually, completely. Within less than a minute, the entire structure falls into the Ohio River. Cars, trucks, people, all pulled down with it. 46 people died. So what happened? The Silver Bridge wasn't old in the way you might expect. It had been built in 1928, not ancient, but not modern either. Its design used something called I-bar chains instead of more redundant support systems. Here's the key issue: the structure had very little redundancy. In simple terms, that means if one critical component failed, there was nothing to take its place. And that's exactly what happened. One single I-bar, a metal link about the size of your arm, developed a tiny crack. We're talking millimeters. The crack was caused by a combination of stress corrosion and metal fatigue, basically long-term wear and environmental damage, and it went unnoticed. Back then, inspection techniques weren't advanced enough to detect such small internal flaws. When that I-bar finally failed, the load shifted instantly to other parts of the structure, but they weren't designed to handle it. The collapse was sudden and total. No warning, no time to escape. The aftermath changed bridge engineering forever. New standards were introduced, requiring redundancy. So that one failure wouldn't lead to total collapse. Inspection methods improved. Monitoring became more rigorous. Silver Bridge is a powerful example of something engineers take very seriously today. Single point of failure, because sometimes it doesn't take a massive mistake, just one small hidden flaw in exactly the wrong place. Alright, this one hits differently, because it's not some remote facility or extreme environment, it's just a building. April 24, 2013, Dhaka, Bangladesh. Morning rush. Thousands of garment workers are heading into the Rana Plaza. The day before, something alarming had already happened. Cracks appeared in the walls, big cracks. Shops and a bank on the lower floors immediately closed. People were told the building wasn't safe, but the factory workers, they were told to come back the next day anyway. Why? Deadlines, pressure, money. So that morning, over 3,000 people went back inside a building that everyone knew was damaged. And then it collapsed. Not slowly, not partially. The entire structure pancaked down in seconds, floor after floor, crashing onto each other, trapping thousands of people inside. Rescue efforts began almost immediately, but the scale was overwhelming. Workers, volunteers, even ordinary citizens rushed in to help, digging through rubble with bare hands. Some survivors were pulled out of the daze, others never made it. The final death toll exceeds 1.1 thousand people, with over 2.5 injured, one of the deadliest industrial disasters in modern history. So what went wrong? A lot. The building wasn't designed for heavy industrial use. It was originally intended for shops and offices, not massive textile factories filled with heavy machinery. Extra fluids had been added illegally. Construction standards were ignored, and perhaps most importantly, the warning signs were clear: visible cracks, structural instability, but economic pressure overruled safety. Rana Plaza became a global wake-up call. It exposed the hidden cost behind fashion, the human cost. After the disaster, international pressure forced changes, better safety inspections, stricter regulations, and global agreements to improve working conditions. But even today, it raises a difficult question. How many warning signs does it take before people are willing to stop? Now let's go back to 1937. Air travel looks very different. Instead of airplanes dominating the skies, giant airships, ziplines, are the future. And the most famous of them all, the LZ-129 Hindenburg. It's massive, luxurious, almost like a flying hotel. On May 6, 1936, it's arriving in New Jersey after crossing the Atlantic. Passengers are preparing to land. Everything seems normal, and then, suddenly, fire. Within seconds, flames sprayed across the airship. Hydrogen, the gas used to keep it afloat, is highly flammable, and once it ignites, there is no stopping it. The entire airship is engulfed in fire. It crashes to the ground in less than a minute. The scene is chaotic, terrifying. People jumping, crew trying to escape. Out of 97 people on board, 36 died. Now here's what makes this disaster so significant. It was caught in film. For one of the first times in history, a major disaster was recorded and broadcast to the public. The famous radio broadcast, "Oh, the Humanity," captured the shock to the moment. But what caused it? That's still debated. Possibly causes include static electricity, a hydrogen leak, or even sabotage. But one thing is clear, using hydrogen instead of safer helium made the disaster far worse. Why hydrogen? Because helium was expensive and controlled by the United States at the time, so a safer option existed, it just wasn't used. The Hindenburg disaster effectually ended the era of passenger airships. Almost overnight, public confidence disappeared, and airplanes took over the future of air travel. It's a powerful example of how one moment, one highly visible failure, can completely reshape an entire industry. September 21, 2001. Toulouse, France. At the AZF Toulouse, it's just another workday, until 10:17 am. A massive explosion rips through the site. The blast is so powerful that it registered like a small earthquake. Windows scattered across the city. Buildings are damaged kilometers away. People initially think it might be a terrorist attack. This is just days after 9/11. But it wasn't. It was a chemical accident. Inside the factory, ammonium nitrate, a common industrial chemical, had been improperly stored. Under certain conditions, it becomes highly explosive. Something triggered the reaction, and the result? A devastating blast that killed 31 people and injured over 2,500. Thousands of homes were damaged. Schools, offices, entire neighborhoods affected. Investigations took years and the exact chain of events is still debated, but the core issue is clear: improper handling of hazardous materials, lack of strict safety protocols, and underestimating how dangerous common chemicals can be. Because ammonium nitrate isn't rare, it's widely used in fertilizers. But in large quantities and under the wrong conditions, it became a bomb. ADF is the reminder that danger doesn't always come from exotic materials or complex systems. Sometimes it's something ordinary, handled carelessly. Let's end with a disaster that on the surface seems almost impossible. A hotel lobby, a crowd event, nothing extreme. July 17, 1981, Kansas City, Missouri. Inside the Hyatt Regency Kansas City, hundreds of people are gathered for a dance. Above them are suspended walkways, elevated bridges connecting parts of the building. They look solid, safe, but hidden inside the design, it's a fatal flaw. Originally, the walkways were designed to be supported by continuous rods running from the ceiling, but during construction, the design was changed. Instead of one continuous rod, they used two separate ones. It might sound like a small modification, but it doubled the load on a critical connection point. And that connection wasn't strong enough. That night, as people gathered on the walkways to watch the dance below, the load increased. And then, suddenly, the supports failed. Two walkways collapsed, crashing down onto the crowd below. The result was catastrophic. 114 people were killed, over 200 injured, one of the deadliest structural failures in US history. And what makes it especially tragic is how small the original change was. A design alteration, a miscalculation, a lack of proper review. That's all it took. The disaster led to major changes in engineering practices, especially is how design changes proved and verified. Because one lesson became painfully clear: even small decisions can have massive consequences. Thank you for watching. Leave the comment about what disaster you think the most scariest. And see you next video. Bye bye.